welcome to our Focus on the Alcohol notes. I do a little bit more with alcohols because there's some varieties in the structures, and there's some interesting things about alcohol properties that you need to understand. Many of these things won't be directly tested, but your understanding of them will be helpful for you very often on Regents Part B2 and C questions. Alcohols contain the hydroxyl functional group as their functional group. Some questions will actually ask you about the alcohol functional group, and for Regents purposes, you can also just refer to this as the alcohol functional group. If you go on to take more chemistry classes, you'll hear it referred to as the hydroxyl group. This can be anywhere in the molecule, and there can be more than one of them. Just a reminder, that's what the hydroxy functional group actually looks like. To be fair, there are actually some spare electrons hanging around in this guy. We just don't draw them. So there are actually lone pairs right there. We just tend not to actually show them, so don't worry about doing that when you draw your structures. There are what are called primary alcohols, secondary alcohols, and tertiary alcohols. These are all alcohols that have one hydroxy group. To be a primary alcohol, the hydroxy group is on a carbon that is only directly attached to one other carbon, or directly bonded to one other carbon. Just to go over our naming of the alcohols. This particular 3-carbon alcohol is what we call 1-propanol. There are 3 carbons in it for that propane stem, and then we change that to an ol ending. We want our hydroxy group to have the lowest possible number, so we would number this guy 1, 2, 3. In our secondary alcohols, this is a very similar alcohol. The only difference is I've moved my hydroxy group so that my carbon with the OH on it is directly bonded to 2 other carbons. This molecule will be called 2-propanol. It still has 3 carbons overall, but my OH group is on my second carbon now. In a tertiary alcohol, I had to do a little modification of this molecule because my carbon that has the hydroxy group has to actually be bonded to 3 other carbons in order to be considered a tertiary alcohol. This does affect the name of this molecule a little bit also. The end of this molecule will still be called 2-propanol. But we're also going to have to call this 2-methyl 2-propanol to account for my methyl group that's also coming off that second carbon. All of these examples are what are called monohydroxy alcohols, and they are named by simply putting that OL ending on and using a number to show where that hydroxy group is attached. The dihydroxy alcohols have 2 hydroxy groups. These are named a little bit differently. This particular example up here, I'm going to number in this direction. If I number in the other direction, my hydroxy groups would be on carbon 2 and 3, and I really want them to be on 1 and 2 instead. So what I would actually call this molecule is 1,2-propane diol. So this is a little bit different. We keep that full propane stem, and then instead of just the OL ending, we call this a diol, and that is somewhat of a separate word. You're not actually responsible for drawing and naming these in a test situation, but it is nice to be familiar with them. You will sometimes see them come up in Part B2 and C questions. This molecule right here doesn't matter which way we number because we have a hydroxy group on each of those molecules. This is a trihydroxy alcohol known as 1,2,3-propane triol. That should not have a dash. I don't know why I did that. I apologize. Propane triol. When we're naming these again, if it's a diol, if it's 2-hydroxy, it's diol, 3-hydroxy is triol, and we do not change our typical alkane base. We just use those numbers in front to tell where those hydroxy groups are attached. What is very important to understand about alcohols is the relationship between alcohols and properties. Water, for example, is this highly polar molecule. Hydrocarbons are these highly, I'm actually going to stick with a 2-carbon hydrocarbon, are these, very, very non-polar molecules. So this is very, very polar. This is very, very non-polar, very symmetrical. An alcohol that falls in the middle of these, if you took a two-carbon chain and you put that hydroxy group on it, this is actually ethanol now, which is the alcohol that we drink. Well, not you, but some people. If we chopped this guy in half, we would see that this is a polar molecule. The polarity isn't quite as strong. We mentioned this kind of earlier in the notes, that when you talk about the electronegativity difference in bonds and things like this, this is only really a moderately polar molecule. Intermolecular forces. The intermolecular forces in water are very, very strong, giving it a very, very high boiling point. Water is going to be a liquid at room temperature, as you know, and in order to actually get it to become a gas, you have to put in a substantial amount of energy. A typical hydrocarbon, such as ethane, which I've drawn up here, is going to have very, very weak intermolecular forces. This is a gas at room temp, and it has a pretty low boiling point. It's very easy to vaporize. It's obviously already vapor at room temperature, so its intermolecular forces give it a very low boiling point. Alcohol falls in the middle. Obviously, when you buy beer, or you don't buy beer, but when people buy beer and it's got ethanol in it, that ethanol is a liquid. So we really see some very moderate intermolecular forces in our alcohols. The reason for this is they're really right in between these molecules. They have this OH and this like polar thing going on that kind of makes them like water. But then they also have this hydrocarbon region that kind of makes them like organic molecules or like hydrocarbons. So my physical properties here are going to be kind of a more medium boiling point. And they're going to be a liquid at room temperature, but they're going to evaporate or boil more easily. So they're going to tend to have lower boiling points than just simply water would. Generally, alcohols with up to 4 carbons are very soluble in water. Once you get more carbons than that, your polarity starts to, you start kind of moving toward the nonpolar region, and your solubility in water definitely decreases. The term denatured alcohol, the alcohol that we actually use in class for certain labs is what's called denatured, and it's ethanol that is used for purposes other than consumption. It actually has methanol added to it, which can also be described as wood alcohol, which, as we mentioned in the other notes, will kill you. So when you see that alcohol is denatured, even if it is ethanol, it's actually been treated so that it will be poisonous to drink. This is also the same type of thing that they would do with ethanol fuel additives. One special molecule that's nice to know a little bit about is something called benzene ring. This is a 6-carbon ring. And in this 6-carbon ring, we have something called resonance. There are double bonds between some of these carbons. This double bond really doesn't always stay here. Sometimes it kind of moves here. And same with the other 2 double bonds shown in this structure. This is a cyclic alkane that actually comes up. You'll see rings that look like this. Sometimes we actually just show this as an inner ring to show that those bonds move. You'll see these in a lot of chemical structures for things such as some of the dyes and pigments that we've talked about, and pharmaceuticals. The formula for this is C6H6 because each carbon is able to fit 1 hydrogen after having that double bond and that single bond. This is a very important molecule that is derived from the production of petroleum. So it's extremely important, what we call petrochemical, useful in pharmaceutical production. The making of plastics also uses it very often. Styrofoam depends on this molecule being in it. We'll look at that with polymers. And there are also possible cancer-causing properties involving this molecule. It's often used as a solvent as well for things that are organic because it's very nonpolar. But it can be potentially very dangerous and have cancer-causing properties. You don't actually need to be able to draw a benzene molecule, but it's a nice molecule to be familiar with and to be able to at least recognize as benzene when you see it in a chemical structure.